So good morning, ladies and gentlemen. The next half an hour will be about physical limits of imaging modalities. And in the first year of the curriculum, we plan to speak about CT, PET, and SPECT, and we will divide this talk by two. So the first half about micro-CT will be given by me, and the second half about PET and SPECT will be given by Bernd Pichler. When we talk about micro-CT, we should first be aware that there are very different scanners at the market which can be used for different purposes. And roughly we can say we have on the one hand the ex vivo benchtop systems which offer you a very high resolution down to less than 5 micrometers pixel size length. They are slow. They usually need 10 to 16 minutes or even longer to record an image. And they are usually not gantry based, and you need a very high X-ray dose to investigate the object. On the other hand, you have the in vivo micro-CT systems, which are usually gantry based. So you have the X-ray tube and the detector rotating by 180 or 360 degree. They are often equipped with flat panel detectors. There are also scanners available which have dual energy functions. We will come later to that point. And they offer only a moderate resolution of about 50 to 150 micrometers pixel size length. They are usually also much faster, so you can scan a whole mouse within 1 second up to 10 minutes. And the X-ray dose that you expose usually is lower. Here you have an example of a typical benchtop system for high resolution. You see that in this system, I have to search the, you have the X-ray tube and the detector fixed, and the object is in between and rotates between the X-ray beam, and you can now also move the object to the left or to the right and thus change the distance between object and detector and do some kind of magnification. So in these systems, the spatial resolution mainly depends on the distance between the object and the detector, on the pixel size of the detector, and of course, as always, on the image reconstruction. On the other hand, you have the in vivo micro-CT systems. Some examples are shown here. Here, the spatial resolution that you achieve is mainly depending on the pixel size of the detector. You cannot change it. It's usually fixed, the distance between the object and the detector and the X-ray source. It depends on the image reconstruction. You should always be very careful with the resolution that is given by the manufacturer, because the resolution that is given can be just a reconstructed resolution. It can be the pixel size. And if you really want to know something about the real resolution a micro-CT scanner has, you should always rely on phantom measurements, which is usually done with the pairs of tungsten wires where you measure the minimal resolution that you can achieve. Coming to the point of quantification, the good point is that we can say that micro-CT and CT in general is basically a quantitative imaging modality. That means that the X-ray absorption correlates with the measured signal. And the X-ray absorption, on the other hand, also depends on the photon energy. And we have two important units that you should know. The first one is CT numbers. This is a quantitative unit, but it's not calibrated. So that means it also depends on the energy of the X-ray. It depends on the size of the object and depends on the detector sensitivity. On the other hand, you have the Hounsfield units, which is the clinically used unit. And here the CT numbers are normalized for water being 0 and air being -1000. And this is clinically used, and many preclinical micro-CT systems use these units. If they don't, I highly recommend to convert the images to Hounsfield units by post-processing steps. Particular micro-CT scanners are often not calibrated. This you should know here. So you sometimes have problems by comparing CT numbers from different scans. You should always consider that CT numbers depend on the energy that you apply. Also, it means that if you measure your object at different energy levels, the CT numbers might be different. And you may also consider that if the object is very small or if the power is too high, you may also have a saturation at the detector, which is particularly true for flat panels, which can also strongly influence the linear relation between absorption and density of the object. You should also know about some artifacts that are present in micro-CT systems. The first artifact I would like to speak about are beam hardening artifacts, which are always present. That means that most CT systems just acquire information about the number of photons, but they don't consider the spectral change when an X-ray beam goes through an object. If you apply an X-ray beam on an animal or on a water phantom, you have a selective removal of the lower energy photons, the soft X-rays from the X-ray beam. And this leads to the fact that the linearity that is assumed for reconstruction is not given anymore, so you have a loss of information, and this leads to reconstruction errors. If it's not corrected, the reconstructed attenuation coefficient decreases towards the center of the object. This is usually considered in the post-processing by just using data from phantoms by cutting algorithms. That means usually you would have lower values in the center of an object than in the periphery. But this is not the case. This is easy to compensate. But you also have beam hardening artifacts coming from additional structures which highly absorb X-rays, like bones, or metal artifacts here you see, which lead to some kind of dark and white stripes on the object. And you can also have very strong artifacts coming from contrast agents that you freshly inject, which can also highly affect the CT numbers that you measure, for example, in a tumor, even if this is more than 1 centimeter away from the object. The second type of artifacts that you should know are ring artifacts. You see them here, some kind of ring. You can detect it. You can also see it in the middle of the object. These ring artifacts result from calibration errors for single pixels. This can be caused by a change of pixel sensitivity during or between different scans, for example, due to heating up of the detector. If they are very strong, they can also result from defect detector pixels or even defect detector lines. And what you can do to solve these problems is if they are based on defect pixels, you can interpolate from other pixels, or in the worst case, if they are very strong, you have to change the detector. Another potential problem in micro-CT imaging is the background noise. And you should always know that the background noise in CT increases with increasing spatial resolution if you don't give more dose, and it decreases with increasing current. And in clinical CT scanners, you usually have a background noise between 10 and 30 Hounsfield units if you have a resolution of about 200 micrometers square. But in micro-CT scanners, you can have background noise up to 60 Hounsfield units, depending on the resolution. And for example, if you now want to do molecular imaging, or if you want to apply dynamic contrast enhanced micro-CT scans, you have to consider that, for example, peak enhancement after a contrast agent injection in tumors, for example, of a mouse, often is not higher than 60 Hounsfield units. That means that you're completely moving within the noise level, which makes accurate assessment or accurate fitting of the curve very complicated. This fact is even more complicated by the just mentioned beam hardening artifacts, which can occur additionally. So what you can do to compensate for that a bit is to decrease the energy if you apply contrast agents, that you make a slow contrast agent injection, that you don't have that strong peaks within vessels, so you have less beam hardening artifacts. You can do more averaging between pixels to decrease the background noise, and of course you can also do some kind of beam hardening correction, which unfortunately is not implemented in most scanners. Nevertheless, if you do everything correctly, it works. You can do dynamic contrast enhanced micro-CT scans, for example, and the advantage in this application is that you have a quite good degree of quantitativeness here, and you can image a whole mouse and all organs within one examination. Okay, I just mentioned the dynamic contrast enhanced micro-CT scans briefly, and I would like to say a few words about data processing, not much, because much more is coming in the subsequent talks. Some models that we frequently use, which are quite stable and robust, and this is important if you're dealing with data which has a significantly high noise, is to determine relative blood volume, which you can easily do by injecting a blood pool contrast agent, we come later to that. Then you can do some kind of first pass analysis. The Miles model here, for example, is very suited for analyzing considerably noisy CT data. And then, of course, you can also apply the models that you're also knowing from MRI, like the 2-compartment models and Briggs and Tofts. A very robust form to determine relative blood volume, which is quite accurate, is just based on this formula where you measure the change of Hounsfield units before and after injection of a contrast agent in a feeding vessel and in the target tissue, and just divide the values, the difference in the target tissue by the values in the blood, and taking this, multiplying this by 100, you get to the relative blood volume in percent. And we tried this once for different kinds of tumors with different degree of angiogenesis and vascularization, and we found quite significant correlations within tumors and between tumors, and a highly significant correlation also with histology within few percentage deviations. Another model that works quite well is the first pass model of Miles. Here you assume that during first pass there's no contrast agent extravasation, which of course is not true here. There's 20 to 30% extravasation, but this you take into account. And you just measure the curve, the input curve, in the target tissue and in the blood, and then you can fit the initial slope of the curve, and can determine the perfusion as the maximum slope of the tissue function divided by the maximum peak in the arterial input function. This model works quite well and is really robust and well to use. The 2-compartment models need better data, need high quality curves, and I don't want to go too much into detail. Twan already mentioned it from the pharmacology point of view. It's not much different here. In these applications, you have the plasma volume, you have the extracellular, extravascular space, and you assume an exchange of contrast agent between these compartments which you model. Important differences between the models is that Briggs from 1991 assumes a contrast agent infusion, which makes it better with respect to the beam hardening artifacts because you can slowly inject the contrast agent. Tofts assumes a bolus injection and assumes a predefined arterial input curve. This you should know when you're working with small animals where this precondition may not be given. And there are also newer models where all the input function data is measured and which to this respect are a little bit more quantitative and better adaptable to mice. Okay, the next point that I would like to address is dual energy micro-CT. So there are different micro-CT systems available also from other manufacturers here, which have inner rotating gantry, 2 X-ray tubes, which can run with different energies at the same time, having 2 detector pairs that take the information. And now you have can consider the fact that, as I mentioned, the absorption of X-rays is depending on the energy. That means if you change the energy for the same medium, you may have different absorption. And this is shown here for 65 kilovolt and 40 kilovolt for iodine, calcium, and water. And taking this different can help you to separate these elements in the body and to do some kind of calcium maps, iodine maps, or water maps. This is shown here in a phantom, where you see that there are clearly differences in the CT numbers that you get after measuring. And here it's converted to a calcium map, and here it's converted to an iodine map. You can use that, for example, to get rid of the contrast agent injection scan, like it was done here in a mouse with an atherosclerotic plaque, which was calcified. You see here after contrast agent injection, a bright dot. You don't know, is it contrast agent, is it calcium? You can make a dual energy scan. Just look at the calcium map. You see, okay, here we really have calcium. Of course, you also see the bones. Or you can do an iodine map just to see the blood system. Often you also have to do gating because particularly heart and lungs are moving in the animals. You have to compensate for that. There are different ways how you can do that. In all ways, you need the information about the respiratory motion and the information about the heart action. You can do that by using a small animal imaging gating system, by using electrodes for measuring the heart action, a pneumatic pillow, for example, for measuring the respiratory motion. This works quite well. The only thing that you have to consider is that these wires that are connected to the animal may cause artifacts, beam hardening artifacts in micro-CT, so you have to be careful a bit. Yeah. The other way is that you make intrinsic gating. That means you don't need cables. You just place a region of interest over the diaphragm of the mouse and determine the center of mass when the diaphragm is moving up and down. So you can also get the information about respiration. In principle, you can do the same with the gated data about the diaphragm with the heart here to see the cardiac motion. If you have this respiratory and cardiac data, you then have just to sort the projections and assign them to different gating phases. And based on that, you can do a reconstruction of new images from the sorted projections, which results in one new gated data set that can be then imaged. You can also do prospective gating. I don't come to that point because it's in my hands too complicated to intubate the mice, in particular if you have high numbers of animals. Here's an example how this works. You see it's feasible even in mice with a high respiratory action and a high cardiac action. This is the lung. Here you see an example for the heart. The diaphragm is freezed, as you see, because we only use the projections from the expiratory phase, and then you can just use the cardiac action, see the heart very nicely beating. And you're sensitive enough even to see differences after pharmacology interventions, like it is shown here, where we performed the Dobutamin stress test in the mouse, where you see the increase of the cardiac contraction after Dobutamin injection. With this, I'm already at the end with my presentation about micro-CT. I hope I could show you that CT is a versatile quantitative imaging modality. You should always consider that, CT numbers depend on voltage and detector calibration. You should know that there are artifacts, particular beam hardening artifacts and ring artifacts, and how they derive from. You should know that the background noise is in CT quite high and the sensitivity for iodine is quite low, so that you always have to take this into your consideration when doing CT imaging research. Nevertheless, you can perform perfusion CT. You have the option of doing very interesting dual energy applications and very nice ways to do motion correction or even to assess functional cardiac data. Thank you very much, and with this I stop and give the word to Bernd.
Thank you very much. Yeah, good morning together. I would like to focus a little bit not on CT but on PET imaging, on molecular imaging, and would also like to bring a little bit light into the physical limits of PET imaging. Okay, so when we look at a PET scanner, we have to consider between a clinical and a preclinical scanner that there are major differences. One is the object of interest. In a patient, we have approximately 70 kilograms, and in a mouse, we have only 20 grams. So there's a factor of 3,500 in between of the clinical and the preclinical object. However, if we consider the scanner, like a clinical scanner has a gantry of 70 centimeter, a small animal PET scanner has usually a gantry of 8 centimeter. We win a little bit by reducing this gantry size in sensitivity, so we detect more gammas the closer we are on the object. However, as you see, the maximum what we gain over here is a factor of 9. Another point is that we have the resolution, and the resolution, the spatial resolution, depends hugely on the detector size and on the individual crystals. So having detectors which have smaller crystals provide us usually a higher spatial resolution. However, we can also turn down the sensitivity because we have larger gaps which are non-sensitive to detect gamma rays. And like in the preclinical and clinical systems, we have over here in the clinical scanner a spatial resolution of 5 millimeter, while in preclinical setups we have usually a spatial resolution of 1 to 1.5 millimeter. So this gains us only a factor of 3. So you see, we never reached a factor of 3,500 to have really comparable images in terms of spatial resolution or sensitivity like what we get in a clinical scanner. This is actually a comparison of different scanners, and I don't want to compare really the companies. There are even scanners over here which are not anymore commercially available. I just would like to show you what is important when you choose an animal scanner, what is important for your individual studies. And actually this is something you need to decide what you want to do. Well, the axial field of view is now in nearly all scanners approximately 10 centimeter. So this allows you to scan an entire mouse or a large part of a rat. This might be important if, like what Tuan shows, if you want to see the temporal whole body pharmacokinetic of a tracer, so if you want to see the biodistribution of a tracer, the whole body biodistribution, then you need to have a scanner which allows you to place an entire mouse in the field of view. The other important factor is the transaxial field of view, and that's obviously important, and depending on the animal species you want to scan. If you want to scan a monkey, then you need to go to a larger gantry. If you want to scan rats or mice, then you can literally choose nearly all the scanners. Another point is the spatial resolution. And most of the people who buy a PET scanner, they discuss very detailed about the spatial resolution, but when you compare all the PET scanners, they're in the same ballpark. The spatial resolution is, in my opinion, really not the critical part when you select a scanner, because all the scanners have approximately a spatial resolution of 1.3 to 1.5 millimeter. And I really don't think that in a specific study, you see 0.1 millimeter difference in spatial resolution. So therefore, I would not bother too much as long as the spatial resolution is in this ballpark. A better spatial resolution is always better. What's important is actually the sensitivity, and this determines how long your scan time is, how much tracer you have to inject. And this is a very important factor. We come in a few minutes, and usually the sensitivity of a current small animal dedicated PET scanner in the range of 5 to 10%. And the higher the sensitivity, the better it is for your studies. And then you have the crystal size. Again, they determine the spatial resolution, but also the sensitivity. And we will come also in a minute back to this. So in anatomical imaging, usually what you see, you get. This is completely different in molecular imaging, and I would like to show you this in a few examples over here. This was a mouse glioma study where we injected stem cells, and those stem cells were transduced and expressed a thymidine kinase, and we used FHBG as tracer to detect the thymidine kinase expression. Over here we had negative stem cells which do not express the TK. Over here the positive stem cells which express the TK. So just concentrate on those two PET images. From visual inspection, I would say they look very similar. And if you look over here where the tumor is, you hardly have any signal over here in PET. However, if you go in and draw your region of interest based on your anatomical image, you see that you have a factor of 3 different in quantification. So 3 times more stem cells reached actually the tumor over here in the positive, in the transduced, in the TK expression stem cells, than over here in the control stem cells. So this means just by visual inspections, you have most of the time a very hard time to really get the information you need, and therefore you need to go in and make a quantification by drawing regions of interest, and the best thing is really to have an anatomical underlying information. Another example is shown over here. This is a study from our group where we want to investigate the dopaminergic system. So we used the C11 methylphenidate, the dopamine transporter tracer. And this is a mouse model for Parkinson disease. So we injected 6-hydroxydopa in the striatum to destroy the dopaminergic system. And as you see, the right striatum over here diminish more and more. So if you want to now quantify this reduction of dopamine transporters, you need somehow an anatomical landmark, either by having MRI scans or by having at least a very good atlas which fit over here your PET images. Otherwise, you have a very hard time to define your region of interest and draw a region of interest. Another important part is, as you choose our threshold, this changes dramatically the size of your lesion. And this is shown over here. This is an FDG mouse image, and depending on what isocontour you use, like over here 80%, 50% or 25%, you change the size of the tumor. So if you want to reveal the real size of the tumor, you need an anatomical image. Also, if you want to place an accurate region of interest, you need somehow an anatomical information underlying your PET image. This is again shown over here. Over here, the threshold would be too high, so you overexpose more or less all the organs. And over here, the threshold for your analysis is too low, and then your organ or your tumor shows up much smaller than it really is. So again, you need to normalize all your images based on the injected activity, and then for one study, analyze all your images, or better off, you have an anatomical information. Another important factor is the sensitivity of the PET scanner. And I discussed this already at the beginning of my talk, that depending on the sensitivity, you detect more or less gammas of your scan. So if you have over here a very noisy PET image, and over here a very good PET image with a good count rate statistics, you're either over here for the noisy PET image, you have a low sensitivity scanner, or you have a very short scan, or you injected a very low dose. So in some occasions, you can prolong the scan time to make a longer scan. However, it is not always possible. I will show you in the next slide. The sensitivity of your scanner is usually hardware set, and the dose you need to inject should be as low as possible. So therefore, this, I would like to make again the point that you want to have a PET scanner which has a very high sensitivity. Coming back to the scan time, most of the time, if for static scans, you can choose the scan time you want to have. However, if you do a dynamic PET scan to see the pharmacokinetic of the tracer, the temporal biodistribution of the tracer in vivo, you might be forced to have a scan time or a frame time which you cannot individually choose. So over here you have like a 1 hour scan, and then you frame your 1 hour into small fractions. For example, over here, within the first 60 seconds, you see the distribution. This is the perfusion image, more or less, of the tracer distribution. And then you get more and more specific binding. So you have small individual frames of your entire scan time. And actually, if this small frames are very noisy because you have a low count rate statistics, you get really in trouble to get good quality of data, good frames, images frames. And you have also then a huge problem if you want to do pharmacokinetic modeling, if you have very noisy data. So therefore, I would like to make again the point, I think the sensitivity of the PET scanner is one of the most important factor if you buy a PET scanner, especially if you want to do receptor studies, as I show you later. Another point is for the image quality, the reconstruction programs, and you have usually analytical programs like the filter back projection or iterative programs like OSIM or MAP. You see that the image quality improves dramatically by these iterative reconstruction software programs. However, the computing time is also heavily increased. Like over here you have 1 minute per frame, over here you have several hours per frame, and this is actually something you need to consider depending on what reconstruction you use, and also you need to consider whether your reconstruction algorithm is approved to be quantitative. Coming to the quantification, usually you have a lesion of interest and you want to analyze how much radioactivity is in your lesion. So what's the activity concentration, the quantification of a specific lesion? And now you get into one problem. The lower your spatial resolution of your scanner is, the easier you get into a so-called partial volume effect. And you might notice from the digital cameras, if you have an all-digital camera with very large pixel size, you get not very smooth image. So you get a noisy image, and also you can maybe not distinguish then two objects of interest which are very closely together. So partial volume effect, we consider a significant partial volume effect is if the object of interest is approximately the same size as the spatial resolution. You're quite good off if your spatial resolution is approximately 2 times the object size. And you see this over here, if you do a quantification and you have 3 times a size of an object, 3 times the resolution, then you get nearly 100% of your quantification back. However, if you have only 1.5 millimeter of the spatial resolution, you make a significant error of your quantification. Actually, these are just simulated results. If you go in the reality, this gets even worse, because if you have different contrast ratio of your lesion to background, this can really go down that you can have a recovery of nearly 0%. So just consider over here, this is a volume of 32 cubic millimeter. So even if you have a volume of 1.5 millimeter in diameter, you can have a situation that you have only, with a very good contrast ratio, a recovery of 30 or 40%. Even with lesion sizes of approximately 4 or 5 millimeter in small animal PET scanner, and with a contrast ratio of 10 to 1, you get usually not a better recovery than 80 or 90%. And this is shown over here. This is a study we did with an antibody, and this is the tumor over here. When we do the PET imaging, we got a percent injected dose per cc of approximately 15%. If we take out the tumor, put it in a gamma counter, what is usually considered the gold standard, where we have no partial volume effect, we got approximately 35% injected dose per cc. So you see, you make a quantification error even for this large lesion of a factor of 2. So therefore, always consider the partial volume effect. In the last 2 minutes, I would like to show also that you need, or might be forced to need, the correction, attenuation correction, especially when you use beds like over here, where we have lucite beds. They definitely attenuate. And also from the mice, you make usually, if you don't use attenuation correction, error of approximately 20% in mice. In our lab, we usually use it in mice only if we have like those beds which have a lot of lucite around it. In rats, we always use attenuation correction. So what happens is, over here, when you look at the absolute quantification, these are non-corrected images and these are attenuation corrected images. In a striatum, you have 548 kilobecquerel per cc, and over here in a striatum, 455. So these are not corrected. And the same is over here, the cerebellum. You see that you make a quantification error. If you use only the ratio, what is often done in the brain, striatum versus cerebellum, you don't make any more quantification error, because the entire brain undergoes the same attenuation. This means if you want to have an absolute quantification, in this case, you need to have an attenuation correction. If you just want to make the ratio and just want to just consider the ratio, you might even get very good along without attenuation correction. So therefore, this is always to be considered what you need to do and what you want to do. The other point I would like to make is avoiding mass effect. Don't inject too much tracer. Otherwise, you might saturate your receptors. This is something related what Tuan said. If you have, for example, antibodies which are radio-labeled, you always get from a radiochemist a specific activity. Never inject more than 5% of receptor saturation. If you inject too much dose, like over here, this is the binding potential, then you see that the binding potential goes dramatically down. So therefore, you should always be in this range where the binding potential remains stable, and therefore inject as much as little dose as possible, that you avoid any receptor saturation. Well, the last point is, it's very important. You can have the best scanner, you can have the best setup if you don't think on the vital monitoring, and therefore you need to keep the temperature of your animal stable. As you see over here in this blue curve, it cools down very dramatically within 1 hour if you don't warm your animal, and also if you don't have a feedback loop, you lose temperature of your animal, and this would, especially in molecular imaging, destroy your entire data. So unfortunately, I'm even a few minutes longer than planned, but I thank you for your attention.